Okay, we'll continue our discussion on second lecture, that means differentiability and analytic function. So first of all, will discuss about the Cauchy-Riemann equation. So Cauchy-Riemann equation is basically there is a partial differentiation, and satisfy the condition is actually del u del x is equal to del v del y, and del u del y is equal to minus del v del x. Okay, this is actually called the Cauchy-Riemann equation. And del u del x and del v del y, del u del y and del v del x both are the partial differentiation with respect to x and with respect to y. So in Cauchy-Riemann condition, there is a theorem. Okay, so the theorem is the necessary and sufficient condition for the function w is equal to f of z is equal to u of x comma y plus I into v of x comma y is analytic at any point z is equal to x plus iy of its domain D, is that the four partial derivatives del u del x, del v del x, del u del y, del v del y should exist and satisfy the two equations, that is del u del x is equal to del v del y and del u del y is equal to minus del v del x. So this is the necessary condition of Cauchy-Riemann equation, Cauchy-Riemann condition. So the necessary condition is basically if the function f of z is analytic in a domain D. Okay, so for so there is any point in a domain D, is that the four partial derivatives, you know, del u del x, del u del y, del v del x and del v del y are exist and satisfied the Cauchy-Riemann equation. Okay, this is the necessary condition. And the sufficient condition is if the four partial derivatives are exist and it satisfies the Cauchy-Riemann equation. From this we will say the function f of z is equal to u of x comma y plus I into v of x comma y is analytic. This is the sufficient condition of Cauchy-Riemann equation. Okay, or if f of z is equal to u of x comma y plus I into v of x comma y to be analytic in a domain D, if the four partial derivatives are exist and satisfy this equation del u del x and del u x is equal to vy. This is actually the partial derivative, new notation on partial derivative. Okay, del u del x is equal to ux and is equal to vy, and del u del y is equal to minus vx. So this is actually the Cauchy-Riemann equation. So the function is said to be an analytic if four partial derivatives are exist and satisfy the Cauchy-Riemann equation, and the partial derivatives are continuous in the domain D. Okay, so this is the necessary and sufficient condition of Cauchy-Riemann condition. That means if the function is analytic, then the partial derivative are exist and Cauchy-Riemann equation are satisfied. And if Cauchy-Riemann equation are satisfied, this is the actually the sufficient condition. If Cauchy-Riemann equation satisfied, partial derivative are exist, then we'll say the function is analytic. Okay, so next we are going to discuss about some examples of Cauchy-Riemann equation, analytic function and differentiability. Okay, so let's start with example 1. For the function, okay, here is the example. The function f of z defined by f of z is equal to root over of mod of x into y, so that the Cauchy-Riemann equation are satisfied at the point 0, 0, but the function is not differentiable at that point, or not analytic at that point. Okay, so let's start. So let f of actually we are going to find the function or f of z is not satisfy the Cauchy-Riemann equation. That means What is the Cauchy-Riemann equation? I have mentioned in the previous slide. This is the actually if ux is equal to vy and uy is equal to v. Okay, so that this one is actually if ux is equal to vy and uy is equal to minus va. This is the Cauchy-Riemann equation. If the function is satisfied these two conditions, then I will say the function f of z satisfy the Cauchy-Riemann equation at any points. Okay, so in that question the function is satisfy Cauchy-Riemann equation at the point 0, 2. Okay, so let's start. So let or consider the function f of z is equal to u of x comma y plus I into v of x comma y. Okay, so where u and v are the real function of x and y. Okay, so comparing this equation with the given equation, this one will get u of x comma y is equal to root over of mod of x into y and v of xy. The imaginary part is not here actually, so this it will be actually 0. Okay, so v of xy is equal to 0. So now from this we'll get the partial derivative with respect to x and partial derivative with respect to y. So now at the point origin, that means 0, 0, del u del x. Okay, so del u del x is the partial derivative with respect to x, and this is the mathematical expression of partial derivative or the definition of partial derivative with respect to x. So limit x tends to 0, u of x comma 0 minus u of 0 comma 0 by x is the partial differentiation with respect to x. So at the point x is equal to y is equal to 0, so u of x comma y, the value of u of x comma y, and it will be actually 0. Okay, so for at y is equal to 0, so it should be 0. So u of x comma y is equal to 0, as well as u of 0 comma 0 y is actually 0. So the limiting value, okay, will be 0 minus 0 by x. So at the point x tends to 0, so this limiting value is 0. Okay, so similarly we'll find the partial differentiation with respect to y. So same thing happened in previous one. So okay, so limit y tends to 0, u of 0 comma y minus u of 0 comma 0 by y. So at x is equal to 0, so this function will be 0. So 0 minus 0 by y is equal to 0. So that means the first differentiation with respect to x is 0. The value of second differentiation with respect to y, that is partial differentiation, is 0. Okay, and similarly we have to find the partial differentiation with respect to x and y for the function v. So here the function v is 0. So from this we'll get the first differentiation, either x tends to x and tends to y, and it should be 0. Okay, so del v del x is 0 as well as del v del y is equal to 0. So from this we'll get the del u del x is equal to del v del y, as well as del u del y is equal to minus del v del x. So all the partial value of all the partial differentiation are 0. So that is it satisfies all the equations, okay, or all the conditions of Cauchy-Riemann equations. So that means del u del x is equal to del v del y, and del u del y is equal to minus del v del x. So hence the Cauchy-Riemann equation is satisfied at the point 0, 0 or origin. Okay. So next we are going to discuss about the differentiability and analytic function of f of z. So here f dash z is equal to limit z tends to 0 f of z minus f of 0 by z. So as you know, f of z is equal to root over of mod of x into y by and f of 0 is equal to 0. So at the point 0, so this function is, it should be 0 by z, and z is equal to, you know, x plus I1. Okay, and z is equal to x comma y tends to 0. So what is the differentiability, or the function is exist? This is actually the same. If f dash z is exist, then it is differentiable. If f dash z is not exist, then it is not differentiable. Okay, so here, so that is we are going to find the first derivative of z, that is f dash z, at any point. Say in this problem here the point is 0, 0. Okay, so in this problem we are going to find f dash z is not exist at any point z is equal to 0 or the origin. Okay, so let z tends to 0 along the straight line y is equal to mx. So I will consider this one y is equal to mx. So y, if you will take any other straight line or any other curve on the organ plane passes through the point 0, 0. Okay, so from this I will take a straight line. Okay, so the straight line is y is equal to mx. So this is actually the arbitrary straight line. So if we put m is equal to 1, we will get y is equal to mx, y is equal to x, be a straight line, and which is also passes through the point 0, 0. So if we take y is equal to 2x, that is m is equal to 2, we will get one more straight line, and this straight line is different from the previous one, and which is also passes through the point 0, 0, that is at the origin. And if we take m is equal to 3, we will get another straight line, and this is also different from the first two straight line. Okay, so from this we'll get so for the different value of m, we'll get the different straight line. What is the existence of a function f of z? So the existence of f of x is if there are two different paths. Okay, I can choose two different paths, C1 and C2. I have already mentioned in the in lecture 1, if there are two different paths, C1 and C2, so these two paths is either curve or straight line. So for two different paths, if the limiting value are different, then I will say this function is not exist. And if for any path, in arbitrary path, if the limiting value are same for any path, then we will say the function is exist. Okay, or the limiting value is exist. So I will take here y is equal to mx is a straight line which is also passes through the point 0, 0. Okay, so from this we will go to find the limiting value of f dash 0. So what is the limiting value of f dash 0? So if we put y is equal to mx in this expression, that is the limit xy tends to 0, root over of xy by x plus iy, we will get limit x tends to 0, root over of mod of mx square by x plus I mx. Okay, and after cancelling the term x on numerator and denominator, we will get root over of mod of n by 1 plus I. So this is the expression of f dash 0. Okay, so in this expression there is only the value of m, but no x or y is exist in this function or in this expression. So if we put m is equal to 1, what we'll get? We'll get of f dash 0 is equal to root over of 1, that is 1 by 1 plus I. Okay, if we put m is equal to 2, what we'll get? We'll get root over of 2 by 1 plus 2i. Okay, so for the different value of m, we will get the different value of f dash 0. So this is the expression of existency. So if for the different value of m, we will get different value of the function or limiting value of the function f dash 0, then I will say f dash 0 does not exist. Okay, that is, thus the function is not differentiable at the point origin. And if the function is not differentiable at the point origin, so we will say this function is not analytic at that point. Okay. So next we are going to discuss about some more example on Cauchy-Riemann equation and analytic functions. So here is the example, and example 2 actually. So that the function f of z is equal to sin x cos y plus cos x sin y, sin hyperbolic y, okay, is continuous as well as analytic everywhere, and find its derivatives. So first of all, we are going to find the partial differentiation with respect to x and respect to y for u and v, and if it satisfies the Cauchy-Riemann equation, that is del u del x del u del y and del v del x into del v del y, then we'll say this function is analytic, otherwise it's not analytic. Okay, so let's start with the solution. So here f of z is equal to u of x comma y plus I into v of x comma y. So comparing this equation with the given equation, we will get u of x comma y is equal to sin x cos hyperbolic y, and v of x comma y is equal to cos x sin hyperbolic y. So u and v are actually the real functions. So in a real function or real plane, sin x, cos x, e to the power x, so all transcendental functions are continuous. Okay, so here sin x is a transcendental function, and this it will be continuous function. Okay, so the boundary of sin x, -1 to +1, and similarly cos hyperbolic x, cos hyperbolic y, sin hyperbolic x are all the continuous functions. Okay, so here u of xy is equal to sin x, and there is a properties of a continuous function. If u and v are the continuous function, then their product is also continuous, this summation is also continuous, and the division is also continuous. U by v, where v not equals to 0, is also continuous function. So here u of x comma y is equal to sin x into cos hyperbolic y. Sin x is continuous function, cos hyperbolic y is continuous function. So that's why sin x into cos hyperbolic y is continuous function. Okay, according to our continuity of properties of continuous function. Similarly, v of xy is continuous, cos x is continuous, as well as sin hyperbolic y is continuous. Okay, so clearly u and v are continuous function for all values of x and y. So u and v are continuous, so by properties of continuity, f of z is continuous everywhere in the complex plane. Okay, so next we are going to find the Cauchy-Riemann equation actually, or the analytic functions. So this is actually the sufficient condition of analytic function. What is the sufficient condition of analytic function? If the Cauchy-Riemann equation is satisfied as well as the partial derivative are continuous, okay, then we'll say the function is analytic. Okay, so let's start with find the partial differentiation. So first of all, we this is actually the partial differentiation with respect to x. So the derivative of sin x, partial differentiation is basically not a ordinary differentiation. When we differentiate partially with respect to x, where y is constant, and if we differentiate partially y, then x is constant. This is actually the partial differentiation. But in ordinary differentiation, when we differentiate with respect to x, then y is not a constant, y is also the variable. But in partial differentiation, if we differentiate with respect to x, then y is constant, and if we differentiate with respect to y, then x is constant. Okay, so here del u del x is equal to cos x into cos hyperbolic y. Why it is cos x cos hyperbolic y? So if we differentiate u with respect to x, that is cos hyperbolic y is fixed. So only differentiate with for the function sin x. Okay, so derivative of sin x is equal to cos x, so cos x into cos hyperbolic y. So similar thing is happen in the second differentiation. Del u del y is equal to sin x into and cos hyperbolic y. Differentiation of this is equal to sin hyperbolic y. There is no negative sign actually, but in differentiation of cos x is actually minus sin x. But cos hyperbolic y is not negative sign. With negative sign is always the positive sign. Okay. So similarly, we are going to find the del v del x and del v del y. It's similar as the previous two differentiation. So del v del x is equal to the differentiation with respect to x for the function cos y is minus sin x. The sin cos x is equal to minus sin x. Similarly, this one del v del y is equal to this. Okay. So from this we have to see that del u del x is equal to del v del y, and del u del y is equal to minus del v del x. Okay. So that is the Cauchy-Riemann equation is satisfied for the function f of z on any point in the complex plane. Okay, so next we are going to find this partial differentiation are continuous. If the partial differentiation are continuous, then I will say the function is analytic. Okay, so next slide will find that the partial differentiation are all continuous. Why they are all continuous? So similar thing is happen for when u of x and v of x are continuous. Why u v are continuous? So this function are all continuous. So similar thing is happen on their partial differentiation. So del u del x is equal to cos x cos hyperbolic y. This is also continuous function. Why? Cos x cos hyperbolic both are continuous. Del u del y are continuous function is continuous function, while sin x sin hyperbolic y is continuous. Minus sin x sin hyperbolic y is continuous. Cos x cos hyperbolic y is continuous function. So all the partial differentiation are all continuous. Okay, so the function, so from this we'll say the function f of z is analytic. So this function is satisfy the Cauchy-Riemann equation, as well as the function is satisfy the partial differentiation are all continuous. So from this we'll say the function is analytic at any point in a domain D. Okay, next we are going to find the analytic function of f of z. So what is analytic function? So if I have already discussed in this class in the beginning, if f of z is analytic function, then f dash z is equal to f dash z is equal to ux plus I into v of x, or if we put ux is equal to vy, that is vx minus I into u of y. Okay, either f dash z is equal to this or this. After using the Cauchy-Riemann equation. Okay, so here I will take only the differentiation with respect to x. So f dash z is equal to del u del x plus I into del v del x. Okay, so here del u del x is equal to cos x cos hyperbolic y, and del u del y is equal to minus I sin x sin hyperbolic y. So this is actually the analytic function of f of z, and it will be f dash z. Okay. So next I'll take one more example on differentiability or analytic function. So here is the example. So that the function f of z is equal to xy plus iy is everywhere continuous but not analytic. Okay, so this function is continuous but not analytic. Said the function is continuous, that means u and v are continuous function, but the function is not differentiable or not analytic. That means their partial differentiation are not exist either, or the Cauchy-Riemann equation is not satisfied. Either any one of this condition is not satisfied, then I will say the function is not analytic. Okay, so this is actually the sufficient condition. If either partial differentiation are not exist, or the Cauchy-Riemann equation are not satisfied, so then we'll say the function is not analytic. Okay, so let's start with consider the function f of z is equal to u of x comma y plus I into v of x comma y. Okay, so comparing this equation with the given equation xy plus iy, we will get u of x comma y is equal to x into y, and v of x comma y is equal to y. Okay, so any polynomial function is continuous in the real plane. So xy is a polynomial function of xy. V of xy is equal to y is also the polynomial function in y is actually. So both function are continuous function in the real plane. Okay, so So u of x comma y is continuous, b of x comma y is continuous. So we can apply the some properties of continuity. So if the two functions are continuous, then their derivative are also their sum, product, division, or subtraction are all continuous functions. So that's why the f of z is continuous everywhere in the complex plane. Okay. So next we are going to find the analytic. Analytic. This function is analytic or not. So we'll start with the partial differentiation of this function. So what is del u del x? So del u del x is equal to y. After differentiation with respect to x, we'll get y. Del u del y is equal to x. Okay. Similarly, del v del y x is equal to 0. So the v of xy is equal to, this is a function of y only. So del v del x is actually 0. So y, when y is constant, and del v del y is equal to 1. So from this we will get del u del x is not equals to del v del y, and del u del y is not equals to del v del x. Okay, so it will be equal, or this condition are satisfied if y is equal to 1 and x is equal to 0. Otherwise this function is not continuous, is not satisfied. So the Cauchy-Riemann equation is not satisfied for any arbitrary value of x and 1. So hence the Cauchy-Riemann equation is not satisfied everywhere except at the point y is equal to 1 and x is equal to 0. At x is equal to 0 and y is equal to 1, this function, so, or this condition are exist. Okay, so at y is equal to 1, that is 1 comma 0, at the point 1 comma 0, the Cauchy-Riemann equation is satisfied, that is the function is analytic. But the function is not analytic everywhere. So everywhere means there are infinite number of points in the complex plane. Okay, so except 1 comma 0, the function, this function not satisfied the Cauchy-Riemann equation. Okay, so this function is not analytic at any point except x is equal, except 1 comma 0 in the complex plane. Understood? So next we are going to discuss one more example. I think this f z is equal to x to the power 3 1 plus I minus y cube into 1 minus I by x square plus y square when z is not equal to 0 and is equal to 0 when x is equal to 0, z is equal to 0. So it's continuous everywhere, but f dash 0 does not exist. So Cauchy-Riemann equation is not satisfied at that origin. Okay. So this function is continuous, but the f dash z is not exist, that is, it not satisfied that Cauchy-Riemann equation. Okay, so let's start with the continuity of this function. So here u of x comma y is equal to, after simplifying this, we will get u of x comma y is equal to this x minus y cube by x square plus y square, and b of x comma y is equal to x cube plus y cube by x square plus y square, and is equal to 0 when z is equal to 0, as well as b is equal to 0 when z is equal to 0. So both functions are continuous function when z is not equal to 0. Okay, so this expression when x square plus y square is 0, then this expression is undefined, so this is not continuous. So this function is continuous except at the point 0 comma 0. Okay, so consequently the function is continuous at the point origin, thus f of z is continuous everywhere. Okay, this is the continuity of the function f of z. Okay, next we are looking for the differentiability and the Cauchy-Riemann equations. Okay, so now at the point is your origin, del u del x is equal to, okay, after cancelling the x we will get 1, and del u del y is equal to, if we put x is equal to 0 in the given expression, we will get minus 1, del v del x is equal to, this is actually the mathematical expression of partial differentiation, and from this we'll get 1, and del v del y is equal to limit y tends to 0, v of 0 comma y minus 0 comma 0 by y is equal to limit y tends to 0, y by y is equal to 1. So at the point 0 comma 0, the Cauchy-Riemann equation is satisfied. So del u del x is equal to del v del y, and del u del y is equal to minus del v del x. Okay, and this function is not analytic at the point 0 comma 0. So why it's not analytic? So this is actually the there is a condition of the analytic function. If the function is is not analytic, that means if for different path the functional value are different, then I will say the function is not analytic function. Or this if that 0 is not satisfied. Okay, so first of all we will take y is equal to x, and this function is also passes through the point 0 comma 0. Then if we put y is equal to x in this expression, this is the differentiation is actually, okay, we'll get the value is 1 minus I by 2. And again I will take y is equal to 0 along the straight line. This is actually the straight line along the origin. Okay, so and it is also different from the first straight line. This is actually the straight line which is passes through the origin as well. So from this we'll get the value of this of f dash 0 is 1 plus I. So for two different paths, and which path and these two paths are all passes through the point 0 comma 0, we'll get the two different values. Okay, so that's why I will say f dash z is not exist at the point 0 comma 0. That is, the function is not analytic. Thank you.